Quasiparticles that are difficult to move easily ascend the pyramid's edges. This is an example of a stride in the generation of computing. Greetings and salutations to everyone. The subject of our video today is a team of scientists that observe a significant violation of Einstein's law of the motion or kinetic theory. This theory is used to describe the way particles spread out in space and were used to move excitons in smaller packages than previously possible. The pyramid-shaped structure was constructed in the Lurie nanofabrication facility. Computational power derived from a combination of light and chargeless excitons could reduce heat loss while also providing additional power, but excitons need new means of transport. Without further ado, let's discuss this captivating topic. Combining light and lack of charge in computing has the potential to mitigate heat loss. However, this necessitates new methods of transportation. Watching a significant deviation from Einstein's law, which describes the spread of particles in space, the team took advantage of it to transport electrons in smaller entities that were previously impossible. Parag Deotare, the study's co-corresponding author and the director of the experimental work, remarked, "Nature employs excitons in the process of photosynthesis, whereas we take advantage of them in the creation of OLEDs, LEDs, and solar cells. The capacity to maneuver stimuli strategically will augment the effectiveness of current devices that utilize excitons and will expand their range of application to include computing. An exciton is primarily an electron that is entwined with a positively charged void in the material's lattice. This has significance in this context. This quasi-particle avoids the loss of energy associated with parasitic capacitances. It has no net electrical charge and is therefore unable to conduct electricity. Additionally, excitons have a simple conversion from light to and from energy. This paves way for effective and swift computers that utilize optics and excitonic principles. This amalgamation would facilitate the theoretical possibility of quantum computing at room temperature, according to Makilo Kira, the study's co-corresponding author, who oversees the theoretical aspect. Excitons function as messengers of information that is retained for a longer period of time than electrons in a semiconductor. However, this is still within the picosecond range. The use of femtosecond laser pulses is being studied to facilitate an efficient process of information storage. Kira explained, "Fully integrated quantum information applications have issues because of the rapid loss of quantum information in conventional electronics. We are currently evaluating light wave electronics in order to augment excitonics with a rapid processing capacity. However, the lack of net charge is problematic in the mobility of excitons." Previously, Deotare participated in a research project that employed acoustic waves to propel excitons through semiconductors. Currently, a pyramid-shaped configuration allows for more precise transmission of fewer excitons, which are confined to one dimension similar to a wire. In practice, the team utilized a laser to create an exciton cloud at the base of a pyramid's corner. This promoted electrons from the valence band to the conduction band. The semiconductor, which is 3 atoms thick and is composed of tungsten diselenide, is covered over the pyramid and experiences stretching that alters the landscape of energy experienced by excitons. Despite the conventional belief that gravity is the dominant force in energy landscapes, it's the semiconductor's band gap that determines how electrons and holes move. The contracted energy gap causes the migration of excitons to the edge of the pyramid. There they seek to ascend to the apex. A formula attributed to Einstein accurately describes the diffusion and drift of particles, usually. However, imperfections in the semiconductor serve as traps that impede the exciton's movement. As a result, the distribution of excitons is anomalous, which indicates an error that is greater than 10 times the original value in Einstein's law. Matthias Florian, the co-first author of the study, explained, "We aren't challenging Einstein's hypotheses, but we have demonstrated that his theory shouldn't be directly applied to complex situations like this one in order to predict the mobility of excitons." To directly observe both phenomena, the team observed single photons that were released during the recombination of electron and hole. Time of flight measurements allowed for the precise determination of the photon's origins. This facilitated the measurement of the distribution of excitons in the cloud. The investigation was funded by the Army Research Office and the Air Force's Scientific Research Department. The pyramid structure was created in the Lurie nanofabrication facility. The team has applied for patent protection with the help of Innovation Partnerships and is seeking partners to help them monetize the technology. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.